Yeah, I'm hilarious. You haven't learned that yet? Okay. And then the disclosure document quiz has to be done by the 1st as well, okay? Couple things, because most of you guys are way better students than I ever was. We're gonna do a lot of graphing today. I always have scratch graph paper here. Some people like to do it on this, and then I've got glue sticks and scissors over there. You can glue them in later if you want, or if you're fine with sketches on your paper. They're still probably gonna be better than the ones I put on the boards because you guys are awesome, okay? Okay, we're going to review all of rational functions, your 3 or 4 week unit, in the next 75 minutes, okay? Booyah, baby. Okay, rational means fraction. Now, everything we do today is non-calculator. You're welcome to check graphs at the end with your graphing calculator. Don't forget to put the numerator and denominator in parentheses. If I'm walking around and I see something like -1 times 6 in your calculator, then I'm going to make fun of you. Okay, this is your warning, okay? We need to review our arithmetic in here, okay? So, let's say, hopefully you guys did your review last time. Let's say that I got, let's start with the fun one, shall we? Did we get to any review last time or hardly none?
We did like one.
Did I talk about holes at all?
Yeah, you said.
Okay, we're just gonna start like we haven't done it at all, okay? All right, so, but it's not like totally from scratch, right? Because you all did your homework last night. Okay, so we have this, factor it. Okay, sometimes I start talking about little things that you don't need to write down, like I make fun of you about stuff. That's my teacher way of giving you time to factor and do other things. So you should be factoring while I'm talking right now. Every math teacher you've ever had has said, well, factoring is the most important thing we're going to learn. They were right. I refuse to go over quadratic factoring in calculus. Okay? If you can't do it good, then figure it out. Okay? Go home and read, study. Khan Academy is good. Okay. Here we go. Gone, right? Okay. What happens with that?
There's a hole.
There's a hole. Where is the hole?
Where x equals -2.
When x equals -2. How do I find the y coordinate of the hole? And why? Plug in -2 for x, I hear over here. Okay. -2 squared minus 4. -2 squared plus...
You have to plug it into the new equation.
Oh, wait, what? Why do I have to plug it in? Hold on, is it a new equation? Let's be careful.
No, it's the same.
No, it's a reduced equation. Okay? It's not exactly the same though, because it doesn't have a restriction. This is not the graph of our function. This is. But this is the graph of our function for every coordinate location besides the hole, right? Because technically the hole's not there, okay? What's going to happen if I plug it in up here?
Then you'll find the coordinates.
It'll still be 0 over 0, right?
Yeah.
Okay, so I plug it in down here. Good. So -2 minus 2, -2. Hold on, where did the -2 come from?
That's from, we're plugging it in.
But how did I know to plug in -2?
Because
That's the 0 of the whole, of the common factor that was reduced from the numerator and denominator. That's its 0. Okay, so I plug that in and I get -4 over -1, or 4, right? So the location of my hole is -2, 4. The hole is a point. It needs a coordinate location, okay? Where's the vertical asymptote?
-1.
X equals -1. It's a vertical line. It needs a vertical line equation. Good. Okay. Now, hold on. We can't, so in this class, more important than other math classes, you know how were you like, your teachers last year, I might have given you this soapbox talk last time, just pretend like I didn't, I don't care, okay? So your teachers last year, right, they taught you about logs. You learned their properties, you learned how to graph them, then you moved on, right? Then you learned about rationals, you learned the properties, you learned how to graph them, then you moved on. Everything's compartmentalized, right? Sometimes you can get through compartmentalized units without really understanding why things are happening, okay? It's not gonna work in here, okay? So I need you to understand why things are happening. So here's my question I'm gonna have you guys discuss with your groups for a little bit, and then we're gonna talk about it, okay? Both a vertical asymptote and a hole are found because of a divide by zero error, correct? So how can the same mathematical error display two different types of graph features? How can that happen, and why does it happen? Why can a divide by zero error give me either a hole or a vertical asymptote, and why is it happening? Why is one the hole and why is one the vertical asymptote? Does that make sense what my question is? I'm going to talk with your groups for like 30 seconds or a minute, and then we're going to talk as a class.
It's like it's moved over and then it's divide by zero. So like this is where it's cross. Well, I mean, like, yeah. No, what they normally that would be that's where the line is. You can make the numbers.
Summers has a funny way of making you realize you don't understand things you thought you did, right? Okay, keep talking. Yep. Uh-huh.
Because since it's making the denominator the bottom line, the denominator at the bottom so when you're you see, so okay, I think 50%. So when you have that's still something that is
I think it's almost like that.
you still have like it's still going to be even if it's
Okay, let's come back together. What do you think? What's the key? Anybody have any ideas? What's the key? Why is -2 where a hole happens, but -1 is where a vertical asymptote happens? Why? What do you think? Here.
Because there is a coordinate for -2 on the numerator, it just gets crossed out.
It all has to do with the numerator. That's the key. When we say crossed out, what do we mean?
Like divided.
Divided away, cancels, multiplying by 1,
Yeah.
right? Okay, I want you to think of this, okay? Let's say I was going to plot some points, all right? Let's say I wanted to know the location of a random point at 5, okay? Let's say I plug 5 into the original equation, okay? If I do, I get 25 minus 4, that's 21, right? Over what? 25 plus 15, what, 42? Is that right? That doesn't feel right.
Yeah, wait.
Oh, yeah, no, that's right, because it's going to reduce. I was thinking 20, I needed it to reduce. Okay. Whew. All right. It reduces by 7, right? So that's 3/6, right? Is that fair? Now, let's say I plug that 5 instead of the original equation. I plug it into the one with the reduced factor. Well, 5 minus 2 is 3. 5 plus 1 is 6. Why was it the same thing no matter which one I put it in? Here.
Because they don't like actually delete, they're just equal to like a 1 basically.
Yes. This half of this rational function, it's like it's not even there. It's timesing by 1, right? It doesn't change if it's there or not there. It doesn't change what the value of the y coordinate that I'm plugging in is, right? Does that make sense? I guess that would go to 1/2, my bad, whatever. That's not the point, okay? So, do you see it? Okay? If I plug in like 1, whether I plug that in up here or just to this, I'm gonna get the same thing, right? Because this is like it's not even there for every infinite value of the domain except for 1, -2. -2 is the only value in the domain that this matters that it's there, right? So it's like I'm just graphing this rational function. Doesn't matter, okay? Why does this one create a vertical asymptote? Because this one does change the number if it's there or not, right? So it's affecting the whole shape of the graph still, which is why it's creating a vertical asymptote. What? Questions? Okay, we're gonna move on. Let's see what you remember. What's the x-intercept and y? Not the x and y-intercept. Y. Okay? What's the x-intercept and why is that the x-intercept? Okay? Raise your hand. Someone I haven't heard from yet. Here.
It's 2. Or
2?
It's 2, 0.
Oh, okay. I know how to plot a point. Okay. There we go. I just didn't know what to do with a 2. Okay. I agree. 2, 0. Why is it 2, 0?
The numerator.
The numerator? Someone else tell me what she means. What about the numerator? The numerator?
If you do x minus 2 equals 0, it comes out to x equals 0. I mean x equals 2.
What is the definition of x-intercept? Where y is 0, where it crosses the x-axis, which happens when y is 0. What makes a number 0? When the numerator is 0. 0 over a number, 0. So where the numerator is 0, after I've gotten rid of the holes, right? That's the x-intercept's x-coordinate. Because 0 over a number, besides 0, is 0. Okay? Good?
Yes.
Okay. Y-intercept. Someone new. A voice I haven't had the pleasure of hearing yet. Okay? Y-intercept. And why? Yeah.
Is it 1?
Why?
Because horizontal asymptote you figure out from far away, and if you plugged in like a million, say, for each of those x's, then those 2 extra numbers on the numerator and denominator would be inconsequential because this is small, so it would just be pretty much normal.
He's right for the horizontal asymptote. I asked about the y-intercept though. But let's go with horizontal asymptote because what he just said is perfect. Okay? Because look, horizontal asymptote, think end behavior, right? So just what he said is you think about big giant x's, right? These are inconsequential, right? If x is at like 0, yeah, adding 3, adding 2, that changes it a lot. But if x is 100 bajillion trillion, what does adding 2 do to the graph? It doesn't change it very much. So perfect. All that matters is these. And if I divide those, then I get 1. Perfect for that horizontal asymptote. Any questions on that? Okay. When can I do that? I need a rule. When can I do that? When can I just divide those leading numbers? Here.
When they can't have a number in front.
Hold on. You gotta be more specific. What's they, what's it? I need to know exactly what you're talking about.
The variable, or I guess x.
Okay.
The power. The greatest power.
What's the vocab word for that? Anyone remember?
The leading term.
Degree. Okay, keep going.
So as long as like the greatest degree of the denominator and the numerator are the same, then it's 1, unless that doesn't have like a number in front of it. Like if it's a 3 on top, then it would be 3 because 3 divided by 1 is 3.
You got it. Anybody remember what those are called? Coefficients. They're called the leading coefficient. That means the coefficient on the one with the biggest exponent, the one with the degree. Okay? Let's do a little bit of a rule over here. That's not what I meant to say. I'm doing this because just like he said, the rest of this is inconsequential, so who cares about any of that, right? All we care about is the biggest one, okay? So if m equals n, then to find the horizontal asymptote, you divide the leading coefficients.
Oh,
Okay, last thing, y-intercept. Yeah. Where are you getting 0, -2 from?
I plugged in 0 for x because the y-intercept was when x is 0. So I just plugged in 0 for x and solved.
Perfect. If you make x 0, then simplify it, right? Good? It's all coming back to you now, right? Okay, questions? Okay, now let's put all of this together and make a graph of this. So these are my rules I have to follow, so I'm going to plot those first. Okay? That's not right. Get it together, Summers. Okay, that's what I know, right? Hold on. +4.
yeah.
I was putting the graph together in my head and I'm like, danger, danger, danger. There we go. Okay, now I can plug in more points, okay, to get like reference points to see. But the point of what we're doing, right, you graphed these super exactly last year. The point of what we're doing is to get the basic idea. I want to know where are their extrema. Do you guys know what I mean when I say that word? I say it a lot. It's the general term for maxes and minimums. So extreme, extrema, extremes. So like bumps, right? Maxes and mins. So when I say extrema, I mean maximums and minimums, okay? I also want to know end behavior. Now last year you guys focused on left and right end behavior, but what's important to us is also the up and down end behavior, okay? Good? Now, let's take a look here. I need to kind of play connect the dots. This one has to go through these, right? It also has to approach the asymptote. Definition of an asymptote might be different than what some of you guys think of it. Many people think asymptote means a line the graph can't cross. That is not what an asymptote is, okay? That is a special property of one type of asymptote, a vertical asymptote, because it's found with a mathematical error, something that math can't do. But we didn't find y = 1 because of a math error. It was a behavior asymptote. This is what the equation is doing as gets really big. Okay, we call that a behavior asymptote. Sometimes I cross horizontal asymptotes and that's okay. How do I know when I cross it? When I have to. I don't have to on this one, so I'm not going to show you that yet. I'll show you on the next one. I'll have to, okay? Good? Now, this piece here, can I cross the x-axis again over here? No, which means I know it also has to go through the hole. It has to go here. Notice that the definition of an asymptote, remember, is a line that shapes the graph. Every arrow that I draw has to go to a dotted line. Whether that dotted line or that arrow is up, down, right, or left, every arrow you draw must be pointing to a dotted line. Or it's not right. Right? Okay? The arrows have to go to the asymptotes. That's what the asymptotes are. Good? Questions? I'm going to do a little bit of harder one next. Because that's what I'm good at. Let's go a little bit harder. Okay. Oh, yeah. I kind of make them up job as we go, so sometimes it's better to wait to write the problem down until I'm done. Just warning you. Yeah, get it. Oh, okay, let's see how you are over here. Oh yeah, baby.
Oh wait.
No!
Okay. Good to know. Good to know. It goes something right.
Got it right.
Hold on, hold on. Didn't I just tell you not to write them down?
I thought you were done.
So did I. Okay, we'll do this one. Factory of 10 seconds. Just kidding. Like maybe 30. Want some good news? You don't really have to do much cubic synthetic division factoring in here. Everything will either become a quadratic if you take an x out. The only cubic factoring you have to do is a perfect cube, but we'll review that today. You might remember a phrase called SOAP. You might not, and that's okay. Remember, my little tangents like this are 1, because I'm awesome, but also 2, to give you time to work. And I hate silence. Factor, factor. Okay, for real, you're hating me, but I don't even care. So, I want to do that one, but I want to do a different one first. Well, keep it. Just make a little space. We're going to come back. We need the factoring of it. Okay? I need one that has... Crimey of river.
So you
Let's just review cubic factoring right now, shall we? Write it down. I mean, I've warned you many times at this point.
If I have to erase it, so be it.
Yeah. I have a funny way of helping my perfectionist students get over that real quick. Hey, we're going to do this one and again in a second, but I want to talk about this one word. You guys are, I don't want to give it away, okay? We'll talk about it first. Okay, so now factor. Actually, let's factor it together, shall we?
Yeah.
Because you can do the top one kind of easy, right? But then I have a funny feeling you're going to need some help remembering a perfect cube factoring trick. Right? Okay, let's just stop here. Let me give you a chance to catch up. Okay, hold on. Hold on, hold on. Okay, you don't need to do synthetic division. The only types of cubic factoring you'll have to do in my class is ones like this where it's really just a quadratic, or perfect cube factoring, okay? So let's review perfect cube factoring. So if things are in the form x cubed plus a cubed, okay, then it factors into x plus a, x squared minus ax plus a squared. And x cubed minus a cubed is x minus a, x squared plus ax plus a squared. Remember, look here, look. These are the same. X squared, ax, a squared, right? Yeah. To know the signs, that's where SOAP comes in. Same, opposite, always positive.
Oh, I like
Same sign, opposite sign, always positive. Same sign, opposite sign, always positive. Okay? So write down what you want and then we'll apply that to this one. It's all coming back, yeah? Oh yeah, it's all coming back. It's all coming back to anyone? Name it? Celine Dion? Ugh. The youth of tomorrow. Ugh. Just kidding.
Today.
Hey, what's the A? What's the A? 3. Think of this like x cubed minus 3 cubed. Okay, so really this one's going to factor, okay, 2. So x and a, right? So it'd be x minus 3. And then x squared plus 3x plus 9. Same sign, opposite sign, always positive. The 9 is because 3 squared, a squared from here. Okay? Any questions? You guys want one more quick cubic factoring that has no relation to any of this, just to try real quick?
Wait, what would we do next after that?
Oh, good. Oh, everyone said no, it's okay. Love that. What would we do next? Let's go. So, one property of this, okay, of this perfect cubic factoring is the resulting quadratic always has imaginary solutions. And everything we do in AP Calculus is in the real number system. So I don't need to factor more. Okay? You could do quadratic formula, but it's always going to have imaginary solutions. And again, we don't use imaginary numbers this year. Okay? That's in like 2 years Calculus 3. Okay? So now let's start looking here. I know this doesn't factor. Is there any common factors? No? No holes, right? Okay? Good? How many vertical asymptotes?
Just one, right?
1 at x equals 3. Okay? No holes, just right there, so I know I already figured that out. Okay? Take a second and find your x and y intercepts with your neighbors.
Oh wait, it's no, you just divide the x squared to make y 0, right? And you multiply the denominator both by 0 equals x squared. X plus 1. And then you just divide by x squared. I got 0 x squared.
Did you get the same x-intercepts?
You just get 0 equals x plus 1.
Y-intercept? You plug in x is 0, but hopefully if we're looking for ways to save time, if the origin is an x-intercept, guess what? That's your y-intercept. And these are functions, they can only have one y-intercept, right? Should I say that again? If 0, 0 is an x-intercept, and these are functions, meaning they can only have one y-intercept, that's also your only y-intercept, right? So I don't need to take the time to plug in the 0 for the x. But if you did, that's fine. We'll just save time later. Okay? So here's your y and x-intercept, here's an x-intercept. Good? Questions? Bueller? Are you with me? Is anyone paying attention? Oh, okay, thank you. Okay, let's plot what we have. Okay? I've got oh man, I forgot one. Where's the horizontal asymptote?
The half.
Isn't that one?
Y equals 1/2.
Wait, why?
It's an equation. Y equals 1/2. degree, 3 over 3, 1/2. Okay? Okay. Yeah.
If you're finding the horizontal asymptote, do you look at the first equation or the simplified one?
You want to look at the first because the degree is the biggest exponent. And so this, if I'm looking this here, it's not like the first x. The degree of this is still 3. I just have to think about it and multiply it out. So you want to think about the one in standard form. Okay, good. Anyone else? Yeah.
This is just a question about the
Hey, you guys, please. I can't hardly hear.
This is just a question about the graphing. Like on the last one, we had like the one, we plotted the one and it went toward both sides. Why do you have to have the one that goes the reverse direction again?
Ah, what a good question. Okay. Now hold on. They don't always go the reverse direction. Okay. But why do I have the other half of the graph, right? Is that what you're asking?
Yeah.
Okay. When I solved for the math errors, how many were there? On this one, when I solved for the math errors, how many were there? There's just one, right? It's not like on a logarithm, right? Where there's an entire infinite portion of the domain that's a restriction, or on a square root, where I can't have negative numbers, entire infinite portion of the domain is a math error. On this one, I have a finite number of math errors, meaning 3 is the only number that gave me a math error, so it's the only number x can't be. So there must be a portion of the graph everywhere else besides at x equals 3. Does that make sense?
Yeah.
Good question. Okay. Okay, good. What else? Okay, now, let's do the easier part first. Over here, right of the vertical asymptote, do I need to plug in a point to know if it's going to be above or below the horizontal asymptote? Okay, someone is saying no. Someone who said no, raise your hand. Okay, I've heard from both of you guys today. Yeah, here.
Oh, isn't it because it's already on the, you already have one line below it on that left side? Oh,
Well, but I don't know. You can't. Okay, I'm glad we're doing this one next because you can't just memorize it's going to be one above, one below. It doesn't go like that. Okay? So I know sometimes, like, people are like, oh, well, they're just opposite. That's not necessarily the case. All right, here?
It would be the top one because it doesn't have another x-intercept.
That's why. When I solved for x-intercepts, I didn't have any above 3, right? So I cannot cross the x-axis again. And how can I do an arrow towards this line and this dotted line and connect them without crossing the x-axis again? I can't, right? Yes, please.
Yeah, it's the same thing for that what you do for vertical asymptotes, kind of. If you plug in positive a billion, then it's the constants aren't really going to change anything.
Exactly.
It'll always be.
Yeah, so it has to go that way. Okay, good. Okay, anyone else? Okay, now this one I want you to watch what I'm doing first, okay? I have a problem. Because if I'm going to try and come up here and go through these, but remember, anytime I draw an arrow, it has to go towards a dotted line, right?
Yeah.
So do you see the problem? Okay. Or I could come here, right? Hold on. There's something, it starts with an M, that fixes our problem. Something about the squared on the x.
Multiplicity?
Yes. Multiplicity. You guys remember that word multiplicity? When a factor occurs more than once, it has a multiplicity. Right? Like a bounce on the graph. You guys remember that? Like probably call it bouncing. Okay? Let's pause on this and I just want to show you something different for a second. Okay? Why does a multiplicity that's even bounce? Here's why. Okay? Let's say I have something like this. I come here and here's my axes, here's my 0 at -1, okay? You can write this if you think it helps. If not, then just watch. Also, don't forget I record all my videos. Some people like to go back and watch them later for the parts I go fast over, okay? They're all on Canvas. They're not pretty. I press start at the beginning and end at the end. So, I mean, it's literally recording this right now. Hello, you in an hour or two, okay? So, I know this is 0, okay? If, before I square this, it's just linear. If I plug in -2, right? -2 plus 1 is a negative number, right? If I plug in 0, 0 plus 1 is a positive number. There's a sign change, not trig, we're not talking trig, sign, S-I-G-N, plus or minus sign, sign change. Make sense?
Yeah.
When I square that, however, the -1 is still 0, right? Okay? But when I plug numbers in here, even if the parentheses were negative, what happens when I square a negative number? There's no sign change. That's what's creating the bounce. Okay? I plug in a -2, -2 plus 1, -1 squared is a positive number. I still have to get to the 0, because squaring 0 doesn't change that it's 0, but there's no sign change on even multiplicities. You with me? Okay, so what does that affect here? It affects this. On this graph, it has to bounce at the 0, but go through at the -1. Do you see it?
Yes.
Has to bounce at the 0, but go through at the -1. Okay? So, it could happen 2 different ways still. Maybe. We'll see. I'm going to draw 2 graphs, so don't draw it yet. I have to bounce at the 0 and go through at the -1.
Then it's going away from that.
Then it's going away from the asymptote. That defeats the whole purpose of the asymptote, right? Okay, so let's try the other direction. Okay, if you feel like you've already got this and your calculator's handy, feel free to type this in real quick in your calculator just so you can see. I think sometimes that helps. Okay. I have to have an arrow, always has to go through the dotted line, no sign change, go through and go towards the asymptote. That's what that graph looks like. Okay? Notice the problem with the first one that I drew, okay? I'm going to draw it in pink so I can erase it really quick. The problem with the first one that I drew, some people think it's that the reason it can't be the pink is because I crossed the horizontal asymptote. That's not the problem with it, because I can cross horizontal asymptotes sometimes if I have to. The problem with it is that its end behavior is not approaching the asymptote. Got it? Okay. Why I wanted to do this one first, now you guys will realize, okay, there's maybe a method to our madness, okay, is because the multiplicity on this one is not on an intercept, it's on the vertical asymptote. So I want you to see if you can figure out what that's going to change, okay? So now go back to this one. Hopefully you already have it factored. Find all of its information, and I just want you to see if you can put the graph together. I'm going to give you about 4 minutes with your neighbors, okay? 4 or 5 minutes with your neighbors to see if you can put this together based on our discussion. And then try and come up with like a rule. Hold on, pause. Are you guys listening still? Try and come up with a rule, okay, for you know what's going to happen if an x-intercept has an even multiplicity, right? It's a bounce. So try and relate that to when a vertical asymptote has an even multiplicity, because that's what's going to happen on y, okay? On y, on the next one, number y, whatever. Okay, do you guys see what I'm saying? Okay, go. Good. You've got about 4 or 5 minutes. We haven't talked about this horizontal asymptote yet. Try and take our last discussion with when the degree of the top is less than the degree of the bottom. Should we talk about that together? Pause. Let's talk about that together. Pause. What, am I wrong? Do you not want it together?
Do it together.
That's what I figured. Okay. I'm a little spazzy today. My bad. It's okay. It's Friday. Friday. Okay. Hold on. As x gets gigantic, do you agree still that the only thing that matters is the biggest term on the top and the bottom? Okay? So we don't care about any of this, right? Good? So if I'm looking at just the 2x squared and just the x cubed, which one's growing faster? The x cubed. Now, the x squared is still growing, right?
Yeah.
Just not as fast. Okay, so I want you to look at a fraction like this, where the top and bottom are both growing, but the bottom is growing faster. Okay? And then instead of thinking of, do you see how that fits that description? They're both growing, but the bottom's growing faster. Now I want you to step back, and instead of looking at the numerator and denominator separately, think about that number as a whole, as an entire number. What is happening to this number as the growth like this happens? It's getting smaller. What number is it going to get closer to? Zero. When m is less than n, the horizontal asymptote is always at 0. Y equals 0. Okay? When m is less than n, the horizontal asymptote is always at y equals 0. That's the only thing we haven't really talked about for that. So now finish the rest. Okay? Good.
I said 4 plus 2 is 5.
The hardest part about calculus is the arithmetic. Remember that the whole rest of the year, because it's true. Did you just hand in a calculator to do 4 plus 5? Are you doing 4 plus 5 on your calculator? Oh, I'm sure that's just your paperweight. Oh my goodness. Okay. Keep going. For time, I'm just going to periodically put things up here, just for you to check answers. Keep going.
That's a problem.
Yeah, that's a problem. So there is no y-intercept.
Hey, I used to make some problems up here.
Okay, again, keep going. I just have some of the info there so you can check answers.
So is there multiple machines for two? Or is that only?
Yeah.
Oh, yes, the word class.
2 at negative x equals negative 3 and x equals 0.
Oh, I didn't see the X.
Yeah.
I didn't think that was
Yep.
That's right.
Wait,
Makes
where
sense.
was that supposed to be in the last one? Okay, so
There is no multiple
this is okay. So we have, oh, there is, no, so it goes in between these two, okay, so it has to go through the two big ones. Right?
I haven't put the answers up yet, but well, you were looking at me though, okay? Sorry.
Odd, so it has to go. Yeah.
About 2 or 3 more minutes. Okay, get the info and try and plot the graph. It matters. There's 3 parts of that graph.
And behavior, so that's horizontal, just those.
Yeah, like crossing it doesn't matter.
Yeah, that's what I was looking at. Yeah, so just 3 parts. So that's just the X.
Let's see, I think, you know, the exercise, there would be 2 exercises. One of them is.
I've just been looking into that exercise.
So you look at the numerator when it's second, so you see you already have x plus 2, so that means one of them is also, and then the other one would be. Oh, yeah. That would be
Oh, it made sense in my head.
Wait, how did you figure out this math?
There's nothing to talk about. And then.
I guess it could go up.
Well, that means we have a bunch of yeah.
That's what you're saying. You don't treat them. You can't if you need to make it. What's the second one? What's the second picture? There's two.
Oh, and she already said.
Oh no, -1. Or -2. Let's plug in -2. We already know what negative 2 is. Oh, I didn't. I'm my thinking. Let's do -1. I was like, wait a minute. So it's
So, see, you one at the top. I think like 2, 4.
So we had.
Oh, you're right.
Okay, and then we have to plug in.
So you gotta think.
It's just a problem. But like, that's like this kind of problem. Like
Done?
Negative 19, I already got that.
We're gonna start.
Oh, yeah.
Okay?
That means that it was negative, so that means it was
There we go. That's a graph. Did you guys just we're just plugging the endpoints at the end?
What?
Gosh.
It's weird.
Oh, yeah, I can't cross
Ooh, we have to plug a bunch of points on this one, huh? You're welcome. Have to on this one, right? Because it's on the asymptote here. I don't know if it's here or here, right? So tell me a number I could plug in here to figure out if this one goes here or here. 1, okay. Plug in 1. All I need to know if it's positive or negative. I don't care, right? So if I plug in 1, is this factor positive or negative? Positive times and the bottom would be positive times positive and positive. So the whole thing, positive. Right? Okay, now I'm going to do over here. Tell me a number I can plug in over here.
Negative 100.
Negative 100. Okay? Positive or negative?
Negative.
Negative.
Negative. So that's a
So that's a
negative.
positive.
Yeah, so positive divided by
Now, hold on.
Yeah.
Multiplicity, now that I have those two, is going to help me not have to plug in a point here. Now, you're probably like, well, what do you mean? It could still go this way or this way, right? But the multiplicity of the asymptote. This one has an asymptote, this one has a multiplicity of 1, right? This is the key here. There can't be a sign change over the asymptote. So what's the bounce version of that happening? It approaches the asymptote towards the same infinity. Notice this one is approaching the asymptote at a sign change infinity because this one has an odd multiplicity. Let it sink in. I can tell it needs a second, right? This is like an x plus 3 squared, right? So it's like a bounce, but a bounce for an asymptote means they approach at the same infinity because there's no sign change.
Wait, but that's on the other side. Why is it approaching opposite?
Because the x equals 0 had an odd multiplicity, meaning it needed a sign change.
Oh, yeah.
Like it goes through the point instead of bounces.
Okay.
Sign change versus no sign change.
Okay, that makes sense.
You guys remember how you felt last year with trig identities? How you looked at it and even like halfway through the process you were like, I'm not really sure what's happening here. But then if you were doing it right, it all just kind of happened, right? That's kind of how these are too, right? If you're doing it right, it all just kind of works. Okay, good? Okay, we've got 20 minutes and I need 25 minutes for our last problem.
Nice.
Okay.
So, we're gonna go. Again, I know I'm going fast. It's because I don't go this fast on the calculus days. It's just because we're doing a whole review. Or Tuesday, I guess, in here, we're starting our first day of calculus, okay? Now, for this first problem here, well, we're going to stick together for time, okay? So the first thing we're going to do is we're going to factor it. Okay, so take a second and factor that real quick, and then just stop there. I just mostly want you to practice your cubic perfect factoring. Okay?
So we can't have this one. Way longer
Another 30 seconds to finish factoring. Or if you're too slow still because of the summer, copy down my factoring. But you'll get faster later. Okay? So another 20 seconds now to finish factoring or realize you need to work on it and copy down what I did. And work on it at home. Okay, just to give you time to catch up in writing again. I don't know again because I teach this lots of times. I don't know if I've said this yet. Okay, but you need to be doing 30 minutes 7 days a week in here. Okay, now if you take Sundays off, that's fine. Do an hour on Saturday. Okay, but if you get homework done before that time, then you should fill it with review. Either factoring, unit circle, things like that. Okay. Understand if you take a day off here and there, that's fine. Tack the extra 30 minutes on the next day. I plan basically like an hour of homework a class period, okay? But you are not going to get nearly as much from this class if you do 4 hours 1 day a week than if you do 30 minutes every day, okay? Did I give you enough time to catch up? Good. Okay, let's do what we know. Okay? I know that there's x-intercepts at 0, 0, -1, 0, and 3, 0. There's a y-intercept at 0, 0. Okay? There's a vertical asymptote at x equals 1. And there's no holes. Good? I'm going to plot what I know. I know I haven't done horizontal asymptote yet. I'm just going to plot what I know. What I do?
Shouldn't it be x squared plus x plus 1? In the factoring on the bottom. X squared plus x.
Oh, yeah. Nice catch.
Well, that one's always positive though.
Oh, plus x minus. Oh.
Nice.
Oh, yeah.
Okay. Any other mistakes?
I think that's it.
For now. Okay. Now, for this next part, I don't want you to write it down because I don't care if you remember how to do it. I'm going to do it, and I'm going to do it fast. Okay? Last year, when you guys did the situation when m is greater than n, and last year you probably had your teacher, tell me if I'm wrong, but your teacher probably restricted it to when m is greater than n by only 1 degree,
Yeah.
right? Okay, so we don't need that restriction. It's the same idea no matter what, okay? You had to find what's called the slant or oblique asymptote. To do that, you did a process called polynomial long division, right? You don't have to really do that this year. I'm going to quickly go through one. I don't want you to write it down. I just want you to watch so I can go quick and then prove to you why we don't need to do it. Does that make sense? Okay, so if I'm going to take this improper fraction, okay, and I'm going to do its long division, I'd say 8 goes into 12 once, remultiply, subtract, bring down the next piece, right? 45, this is the remainder. I know that's the remainder because I can't go into it again, right? Okay, this is like the 125, this is like the 8. This is the dividend and this is the divisor. I think that's what those words are called. But this is the improper fraction for this polynomial, right? Okay, so I'm going to take it, I'm going to do 3x cubed minus 3, negative 2x to the 4th plus 4x cubed plus 6x squared, and then I'm putting in my placeholders, right? Okay, now I need to take my leading terms again. I don't care if you remember how to do this. I'm reviewing it for the algebra practice, okay? And just trying to jog your memory from last year, so I'm really going to go fast for time, okay? I need to know, how do I get from here to here? Okay, I multiply it by an x. That's what makes the x cubed x to the 4th. I need to get rid of the 3, and I need it to become a negative 2. So negative 2/3 is going to do that. Okay, I take this and I remultiply. So that's 3x to the 4th. And then I also have to remultiply by this piece as well. So that's going to be a positive 2x. There's nothing for those pieces. 3 pass negative 2. Right? Because the 3's canceled and became a negative 2. That's why I did that. Okay, moving on. Okay, that goes to 0. 4 minus 0. 4x cubed plus 6x squared. 0 minus 2. 2x. And I go here. How do I get from 3x cubed to 4x cubed? Well, I don't want any x's. I want to get rid of the 3 and times it by a 4. Okay? Then I remultiply. This is going to be minus 4. I'm bringing down the next piece. And I subtract. Right? So this goes to 0, then I have 6x squared minus 2x plus 4. This is now my remainder because this one's degree is now less than this one's degree. Last year, you realized that this was the equation of the slant asymptote. Right?
Yeah.
Anybody remember what the remainder affected? Nothing, it didn't matter. Now this year, let's understand why. I'm going to take this improper fraction, okay, like the 125 over 8, okay, and turn it into a proper fraction. So if I were going to do that with this one, it would be 125 over 8 is the improper fraction, and a proper fraction would be 15 and math and plus, right? 5/8, or 15 and 5/8. Right? Good? Okay, so let's do the same idea here. The 15, that was my quotient, right? So the proper fraction version of this improper fraction would be negative 2/3 x plus 4/3 plus my remainder, right? Over my divisor.
Oh yeah, we did do that last year.
Where is this one's horizontal asymptote?
0.
Why? Tell me quick.
Because the power of 2 is smaller than the power of 3.
Is it always going to be that way? Yes, because that's when we stopped long dividing, right? When the degree of this was less than the degree of this. That's when we stopped long dividing, which we know it's automatically 0. That's why the remainder never mattered.
That's smart.
Okay? But even more than that doesn't matter, right? Because I don't need to know exactly that this is at 4/3 and then I go down 2 over 3, right? The only part of this asymptote that matters for my graph is its end behavior, right? Because I just want to know where to put the ends of my function. So all I need to do is decide if the quotient of the long division fits into one of 4 categories: positive even, positive odd, negative even, negative odd. Polynomial end behavior.
Yeah.
Is that familiar at all? Right? Up, up, down, down, up, down, whatever dance or whatever, right? This one is a negative odd, right? Negative odd. Negative coefficient, odd degree, negative odd. A negative odd has the end behavior up, down. The end behavior of the rational function will always match the end behavior of the quotient from long division. Let's say that again. The end behavior of the rational function will always match the end behavior of the quotient from the rational function. So how much of this did I need to do to find the end behavior of it? None of it. I could have done that up here. Is negative 2 over 3 a positive or a negative number? Negative. And is x to the 4th over x cubed, when I simplify that to x to the 1st, right? It's an odd. So you never need to do any of this, because I don't care what the numbers are. All I care is what the end behavior of that being divided is. Do I have any of you still? Oh, more than I thought. That's great. Okay, so let's finish graphing this, and then I'll show you another one, and then we'll write a rule. Okay, so this here I know is going to have to go through like this, because at the 3 it has an odd multiplicity. It's got to go through it, and it's got to have that same end behavior and approach the vertical asymptote. Okay. The 0 has to bounce. So sometimes I like to come from here and do the one that goes through, bounce. Notice that should also make sense because that vertical asymptote had an odd multiplicity, right? So notice how the pieces had to approach it at different infinities. Multiplicity affects the vertical asymptote similarly to how it will affect the x-intercepts. Did I blow your mind a little bit today? Yeah? Okay, let's get a rule over here, and then I'll remind you your polynomial ones, and then I think we'll have time for one more quick example, not of all of the graphing, but just of this idea. Okay, so when m is greater than n, okay, I call it the behavior asymptote because it's not necessarily linear. Sometimes it's a parabolic, okay? So I call it the behavior asymptote is the quotient, is the end behavior of the polynomial quotient from long division. That is a lot of math terms right there, huh? You are welcome. For the evens, I like to think of a parabola. And for the odds, I like to think of a linear graph and whether or not its slope is positive or negative. That's how I remember it. Okay? The positive or negative is from the leading coefficient. Is there two F's in coefficient? I don't know. And the even or odd is from the degree. Okay, while you guys write that, let me see if I can come up with a really easy one we can do in 5 minutes. This one should be easy, actually. Not sarcastic. Sometimes when I say that, it is sarcastic. Not this time. For time, we'll still go through it together, but I'm going to give you another 30 seconds to write down what you want. Last year, you guys did a lot of these, right? You did a little bit of watered down versions, and that's okay because it wasn't calculus, right? But this year, I can give you, that's why I make them up on the fly. I can give you any type of rational function, and you can handle it no matter how weird it is, right? Oh, yeah. Okay. Let's start by factoring. The top is already factored. And the bottom factors to x plus 2, x squared minus 2x plus 4. Good? It has an x and a y intercept at 0, 0. That's its only x intercept. Is that good? Okay, it has a vertical asymptote at y equals -2. Why? X equals -2. My bad. And it has a behavior asymptote because it's not a horizontal line and it's also not a slant or oblique, right? Okay. That is negative even. Right? If I take these and divide them, I'd have a negative x squared. Does that make sense? If I were going to go through all that long division, I'd end up with a negative x squared something, right? So my behavior asymptote is a negative even, which means I know it's going to be down, down. Good? Okay, so then if I take my points and I plot them, I know this piece can't cross the x-axis, right? So it have to fit here. And I know this piece, it has a multiplicity bigger than 1. Does that mean it bounces? No. Because it's odd.
Oh, yeah.
Only when it's even does it bounce.
Yeah.
So this one is going to go through at the 0, right? So it has to look like this. Good? Yeah.
Behavioral asymptotes are like the horizontal where you can go through it if you need to.
Absolutely. Okay? Which is another reason why it doesn't care if I know exactly where the inside portion of the behavior asymptote is, because if I cross it, who cares? It only matters at the ends because the arrows at the end have to point to it. Okay? You guys did great, okay? A whole unit in a day. Okay, your homework, you've got 2 options. I might have said this at the beginning. I don't remember. I teach this class lots of times. I get confused, okay? There's a worksheet on Canvas. I was going to do some from the book. I didn't like any of them. I don't care if you print it off or I also sent it out via Remind. You can look at the questions on Remind and you can just do it on your own paper. You do not turn in homework in this class. So some people like to do their homework right by the notes. I come around and I check them every day on like a stamp sheet, but it's up to you to make sure if they're right or wrong, okay? And a lot of people like to use them to study, okay? So you are not going to be ripping it out or turning it in. So you do either print it off or do it in your notes, whatever will help you use it appropriately best. Does that make sense? Any questions? Okay. Do it without your calculator and check them with your graphing calculator. You guys have a wonderful weekend. Great job.